All right, welcome everyone to another instance of our Northwest Database Society Symposium sponsored by Yahoo. And today we are very excited to have a speaker from Amazon, Sailesh Krishnamurthy. That's right, from Amazon. So Sailesh is an engineering manager at Amazon working specifically on a very exciting new project called Aurora, which is one, I think, currently the fastest growing service, right, on Amazon Web Services. So we are very excited to have you here and hear more about this project.
Thank you, Mecca. So thanks everyone for coming to my talk. I'm based actually in Palo Alto. AWS has development teams both in California and in Seattle. My colleague Kamal is here. He's based in Seattle. I lead the Amazon Aurora database engine team. First part of my talk, I'm just going to give a bit of a motivation, a little bit of an opinionated view of why we think building software in the cloud is different, and then I'll get to what we actually did. So first, what is Amazon Aurora? It's a MySQL compatible relational database with the goal being the performance and availability of commercial databases, but the simplicity, cost effectiveness of open source databases. But before we get into that, let's talk a little bit about how you design for the cloud. So this is a little opinionated, but the traditional way, there's a central design constraint, which is the amount of resources you have for building your system is scarce. You could run your software on a single node, on 10 nodes, or 100 nodes, but what you have available is the storage compute and network resources associated with those sets of nodes. And you have to do pretty much, ultimately, a lot of system software, and certainly database system software, is about taking the best use of that scarce system resources. In the cloud, we actually think there's a new way, a big opportunity, which means big challenges, a way to rethink how we build systems. In the cloud, you can actually think of your system resources to be virtually unlimited. So you have abundant resources. So you have actually a new opportunity, which is how do you actually rethink the design of system software in a way that you get to exploit this abundance. So, I'll come back to this theme again later in the talk, but if this is the big idea that animates a lot of what we're doing in database services at AWS. It's all about how you exploit abundant system resources in order to deliver interesting systems for customers. So now let's focus on relational databases, and let's think about reimagining the relational database. If you were to reinvent the database today, our perspective is you wouldn't actually do it the way this was done in 1970. And database systems haven't changed that much in the end of the day from the work at system art. We think you'd build something that can scale out, that is self-healing, and again, slightly opinionated perspective that leverages existing services, AWS services, for instance. So let's take a small digression first into current database architecture. So we think they're monolithic. Kind of a cartoon depiction of them is you have this layer cake with a SQL execution layer, transaction layer, buffer cache, and the logging layer. You have an application that talks to the database engine, but the piece in blue is actually a single monolithic daemon typically. And that talks to the storage layer. Now, most database engines don't really care that much whether that's storage, whether or not the storage is attached or on the network. For the most part, the database engine code doesn't really change. I'm slightly lying here, but not by a whole lot. So people have done various different things to try to take this monolithic architecture and fundamentally solve the scaling problem. So the first thing, which is common for a lot of internet companies, is sharding it. And so people, in Facebook and Google and Amazon and Yahoo, typically take multiple instances of the software, partition the data by some declarative application-specific model, typically by user or something like that. They shard the data. And you have independent instances of the database engine that don't really talk to each other. And instead, these systems are coupled at the application level. So that's kind of a sharding approach. The second approach, and this is common for DSS VI systems, is a shared nothing approach, where the data is again partitioned, the stack is still monolithic, but the application can send queries to any node in the system. And here, the system is coupled with the SQL execution level. So here, you typically have exchange parallelism, Volcano, and all of goes back to the Gamma work. And then there's the shared disk approach, which really was pioneered by Oracle, and I think IBM now has its own version of that. where you have a single storage layer and you have multiple nodes, and the application is able to talk to any node in the system, and it's actually coupled at the caching layer. And so you're effectively doing cache coherence, the buffer pool, and trying to implement some kind of a distributed lock management. So the shared disk approach is useful for OLTP systems, but in today's incarnation, it's quite expensive, requires a lot of custom hardware, and has scaling challenges. So one thing that's common to all of these approaches is that even when you scale it out, you're actually still replicating the same old stack. So going back to the big idea I started with, if you're really trying to break out of this box where you have scarce resources and trying to get to this world where you have abundant resources, it's our perspective that you have to do something different. You have to find a way to break that stack down. And if you don't, you have challenges for cost, for flexibility, and for availability. So, yes, question.
Just curious if you could give us an example to show the difference between sharded and shared nothing, so that we're on the same page as you.
Sure. In the classical example is in the sharded case, right? Let's say you've partitioned your data, let's say for a social network by users. And I want to go and ask information about a particular user. I figure out a way to go to the right shard, so I have a routing problem that has to be solved with the application layer. I can go and run a query on that system to say, give me the information about this particular user. But suppose you want, say, the photograph of that user's friends. Now you have to run first a query to get the user's friends, and then you have to go at the application layer, go and figure out the shards for all of those individual users, those friends, and then go and run a whole bunch of other queries. And all of that heavy lifting is done on the application layer, which is why I'm calling it out as being coupled to the application layer. In the shared nothing system, in contrast, you could just run that query as a join or a self-join, I guess, as the case would be, and the system should automatically take care of rewriting that query, partitioning it, running usual exchange parallelism to run that query in parallel. The shared nothing approach is great at scaling read queries, great at scaling queries that scan over large amounts of data. It's pretty lousy for OLTP transactional work, basically. Okay, so now going to the Aurora architecture. So we're kind of calling what we're doing a microservice approach for the cloud. And this can be slightly controversial. People think of microservices as, by definition, small. But actually, a microservice is not necessarily small. If you look at how people have built applications, and I know it's not fashionable for database engine people to look at the application side, but I think we can learn something from how the application world has happened. If you look at, say, something like Netflix, they've gone from a world where you had a single big monolithic application on a single data store into effectively, a separate data store for users, a separate data store for content, and these are all run as independent services, and you have an application that interacts with these services. There's a lot of good that comes out of separating your systems into individual separate services, or microservices, as you might call them. You get a lot of benefits out of operational convenience. You get to run change management for the user system separately from the content system. It goes beyond modularization. It goes into actually operating these as separate services. And so what we really are looking to do is adopt this notion of a microservice architecture for a database engine, which is a little unique. And so if you look at the Aurora architecture, you still have kind of, the database engine has these three layers, the SQL execution layer, the transactions layer, and the caching layer. But what we did is we took the logging and the storage layer, and we broke it out into an independent, multi-tenant, scale-out microservice that's optimized for OLTP database workloads. So that's kind of the key idea in the Aurora architecture, which is if you can take individual components of that layer cake and find a way to scale them out separately and run them as independent microservices, then you can actually going back to my big idea that I started with, you can actually exploit this power of abundance. We can scale them out separately and separate out concerns. Right now, we've only done this for the logging and storage layer, but our ambitions are really to take this idea and go all the way up the stack. So Aurora is again a microservice architecture for a database engine that interacts with other AWS services such as EC2, VPC, DynamoDB. There's a whole bunch of things. Route 53 for DNS and so on. This question.
So, is there any interaction between the logger layer and transaction layer? Because it seems not very obvious that, when you do transactions, you actually relies a lot on the logging side, right? So when you extract out the logging layer into the AWS or microservice, is there any problem? Like,
You have to do it carefully. We'll get into the details, we'll talk about it. But the higher bit is we figured out how to make logging and storage independent and focus on a very specific concern. And it is about how to write, how to read pages from the storage layer, and also how to send writes in a certain specific way. It turns out what we do effectively is we send redo log records. I'll get to this in just a second.
do you support like distributed transactions?
No, not right now. So we can talk about what that might mean. Let's look into Aurora storage first and drill into what exactly this means. The AWS network architecture is slightly different from what you might normally have, where typically when you go outside a data center, you're operating at a WAN link. AWS has this notion of an availability zone. Each AZ can be thought of as an independent data center, and which is no more than 2 or 3 kilometers from another AZ, but still having more of a LAN quality link as opposed to a WAN link. So the Aurora storage is a distributed system with a large cluster of storage nodes that has certain properties. It's deployed across multiple AZs. It's all implemented in SSD. It's a multi-tenanted system, and it's actually log structured. So let me try to break down each of these things. Writes that come into the Aurora system. So if you think about the Aurora storage, you have a notion of a volume, which is a big space of pages that is striped across this entire storage system. It's multi-tenanted, and so that means multiple separate customer instances, database instances, are all mounted on that same storage system onto separate volumes that are striped across the storage system. It's highly available, and so what we effectively do is the writes that are coming from the database engine to the storage system are replicated across 6 segments. So each page is actually replicated across 6 separate storage nodes in 3 different AZs. What this gives us is effectively when we do writes, we are looking for acknowledgements. We're looking for a 4 out of 6 write quorum. So what this means is you can lose an entire AZ and still have retain 100% write availability. The volumes can grow up to 64 terabytes. One of the big benefits you get from this architecture is that you don't have to deal with provisioning, I/O provisioning anymore. Customers just pay for the actual usage. So some of this is again going back to public cloud economics. One of the nice benefits of public cloud economics is you only pay for what you use. We figured out how to do that actually for the storage layer. So finally, the key idea is about log structured storage. So in a normal database engine, when you're writing to something like EBS or some kind of a SAN, the database engine is actually having a page writer that's going to write 30 pages to disk. In the Aurora storage system, the API that is offered by the storage system basically comes down to a read page, give me a page from a given volume. But the write never actually writes a complete page. And instead, the only thing it actually writes are redo log records. So for those who are not familiar, a redo log record is essentially a diff. You're doing some kind of a DML operation, an update, an insert, or a delete that goes and manipulates pages that are effectively in the database cache. Each of those manipulations, maybe an update of a given attribute of a given row, is going to result in a log record, which is effectively the diff between the before image of that page and the after image of that page. And what we do is only send those diffs. It's only those redo log records that are actually being sent on the wire. The actual storage system itself is a log structured implementation which is able to coalesce the logs on the fly to return a page on demand. So let me stop. This is a key aspect of the system.
Just to make sure, what is the interface here? So interface, read a page?
Read a page. You actually read a page as of a particular LSN so that you can actually get the right snapshot isolation that you care about.
Okay.
And so the storage system is able to coalesce up to that LSN and return the page.
Yeah, and then when you write, you send the...
When you write, you only write the log records.
Okay.
And of course, you do things like batching to make sure you write it correctly. You get performance.
Okay. And my second question, is this storage layer only used by the Aurora service, or is it used by others?
It is not used for anything. It's
Okay.
custom designed entirely for Aurora service. It's really optimized for OLTP workloads. It is, we also, the same Aurora service also, one of the nice things that you get from this whole architecture is you're writing redo log records to the system. Those same redo log records are also streamed to S3 for long-term storage, like for backups essentially. And so that also eliminates a major pain point in an OLTP database engine where typically to do a backup, you have to scan through all the pages on disk and copy them to take a snapshot. In our world, you don't have to do that at all because all you need to do is just stream these same log records out to S3. So you get a lot of very good properties inside. Question?
I don't understand how a 3 out of 6 read quorum is guaranteed to overlap with a 4 out of 6 write quorum.
Well, the write quorum is just telling you that if you so long as you've got 4 acknowledgements, you can make progress. The read quorum establishes when you're actually getting a read request at a particular this layer, a particular LSN, trying to figure out which node is actually having complete set of log records to be able to answer that request. So they're not necessarily interacting with each other. One is more about, in order to satisfy the read, we maintain metadata in terms of, for every given segment, for each of the 6 segments that exist for a given, that host a given page, what is the highest LSN point until which writes have actually made it. And so long as you have at least 3 of them, you can direct your read query to any one of them.
So why is that not 4?
Why do you not need 4?
Yeah.
You just need them to overlap.
Well, you don't need an overlap as such. You actually, so long as you can access, you need 3 more from how the actual replication works to make sure we're able to, like I said, avoid holes. Let me get to that in a little bit. So first, let's talk a little bit about performance. So overall, there are a bunch of different things that we did for performance. One of them is to have fewer IOs to minimize network packets, and also to process data more asynchronously. So there are other things that we've done. For instance, the database engine had, because it's a MySQL-based database engine, had a lot of points of contention with single global mutexes that we went and fundamentally changed. But the big benefits are the 3 things that I'm calling out here. So let me explain again how the system works with a counterfactual. So let's think about RDS MySQL. So RDS is a managed database service offering that we have in AWS. So RDS MySQL is, you have a primary instance and a standby instance, and you're writing to this Cloud SAN EBS, block storage system. And the IO flow is, you have different kinds of things that you're actually going to be writing. You're going to be writing your redo logs. You're going to be writing your bin logs, typically because you're setting up bin log replication, master slave replication. You're also going to actually write the data pages. You do a double write to avoid, don't writes. And there's also catalog data that you write, FRM files. And it's actually fairly complicated because the way you actually get availability is, in addition to the actual write, you write to a standby, you write to a mirrored volume here, and you also set up, use DRBD, which is the kernel level mechanism to actually copy out of the blocks to another standby actual instance. And there's a lot of this stuff is synchronous. So for instance, steps 1, 3, and 5 are sequential. They have to happen in sequence. And this means it's susceptible to, if any one particular path suddenly has a bunch of jitter, then you end up slowing down your entire flow. So this is kind of the counterfactual I'm presenting in terms of what you do today. And so if you look at performance, if you look at something like this, and you run some of the standard sysbench workloads that people do in the MySQL world, you can get about 780K transactions over 30 minutes. Roughly 7 million IOs per million transactions. So about 7 IOs per transaction is actually 7 pages that you're actually going to be writing. So the alternative, if you look at the Aurora alternative, so you have multiple AZs. Effectively, the only writes you're doing is the redo log records. So to again emphasize, in Aurora, the data pages are actually never written to disk. The only things we write are the redo log records and nothing else. And so we have our own read replica infrastructure, and so we also send the same log records that are sent to the data pages, to the storage system, to the read replicas. I'll get into the read replicas a little bit more. But effectively what we're doing is we're taking, if you look at the I/O flow, the right path, we are batching together log records ordered by LSN for a given database engine, and we are writing it out to the storage system. The storage system can get it in a partially ordered fashion, can have holes, in which case it needs to fill in those holes by fetching the log records from peer nodes. So if you think about overall what's going on, every log record is actually written 6 ways. So we have 6x more log records that are actually written. But because we completely eliminated the data pages and the double writes and all of that, we actually do substantially less traffic on the wire. Typically something like 2 to 5% the actual amount of traffic. So you run the same 30-minute sysbench write-only workload. What you would actually get in our system is about 35 times the number of transactions, substantially less IOs that you'll actually end up doing. So you get very big benefits if you think about it. Ultimately, what we've done is gone from a world where you write 16 kilobyte pages, and in an OLTP transaction, you don't get much temporal locality. Your writes are pretty much scattered all over your cache. And so you go from a world where each of your writes into any individual page is pretty much resulting at some point, not necessarily at commit point, but at some point you have to pay the piper. At some point, the 16 kilobytes have to be written on the wire to storage, to a world where you're only writing these log records. And the read log records on average end up being between 100 to 200 bytes. Let's even take 200 bytes. 6 times that is you're writing basically 1.2 kilobytes. So you go from this world of writing 16 kilobytes on the network to a world where you're writing 1.2 kilobytes on the network. That sets up the first big advantage. That's kind of the one big reason in which you get performance. But it's not just about just the sheer amount of data that's actually written out. The other important thing is that all of this stuff can be written asynchronously. And that's where the quorum writes come into play. That as your database workload is generating the writes that you're actually manipulating the pages in the cache, you're forming the flow of redo log records. And you can start sending them asynchronously. You're not really waiting at all. And the way it works is as those writes propagate to the database, to the storage system, acknowledgements keep going back up. And as you keep meeting your write quorum property, you know when it's safe to effectively commit the transaction. And because of this architecture, we are much more able to handle things like temporary loss of connectivity, being able to handle jitter. So there's a lot of logic that happens in the database engine, which is trying to look at, is a particular storage node slow? Do I need to give up on that particular storage node? And maybe that actually is unavailable right now, and then it's up to that storage node to talk to its peers to get the missing log records. So 2 big benefits to summarize. One is just fundamentally far less I/O, far less writes on the wire, and secondly, to be able to get as much asynchronously as possible.
So I have 2 questions. So first one is that it says that in average the I/O per transaction is less than 1. Do you mean you actually do some sort of batching for group commit?
Yes. No, sorry, batching before commit, you said?
Batching for group commit.
We do group commits, asynchronous group commits to acknowledge back, but we do batching, in fact, of log records across different transactions too. So you have many different transactions that are coming here, that are generating writes in many different pages. And so we keep accumulating those sets of log records that have to go to a given storage node, whether they come from one transaction or whether they come from another transaction. We batch all of them, and then we fill up the buffers. And when either the buffers are full or you have a commit, you're going to flush them and write them out. And so you're right that we end up doing, because of batching, we can actually do less I/O per transaction.
So the second question is that you said all states are synchronous, but in order to reach say durability, you need to have at least, I guess you need to have at least 1 writes that are synchronous.
Right, that's the final commit. At some point, we have to actually acknowledge the commits. So let's see. I think let me skip to the next. So we have a notion of how. Let me explain kind of how group commits actually work. Asynchronous group commits work. So on the database engine, you have many different transactions that are doing reads and writes. As the writes are happening, reads are a slightly different story. Reads cannot, be asynchronous because you need to get the data back to the buffer pool in order to do something. But as the writes keep coming in, the writes keep flowing out to the storage system. And now we keep acknowledging something called the durable point as an LSN. So you can think of that as a high water mark. And what that is telling you is all LSNs smaller than that have been durably written. In other words, quorum has been acknowledged. And this moves up like a step function. It doesn't move just incrementally. So every time it bumps up, you look and see. So at this point, you got your durable point moved to 20, and you know that transactions T1 and T2 are ready to be committed, and you go and acknowledge them and commit them. And similarly, the next time to move up to 49, you can go 3, 4, 5, 6, 7 at that. So that's the point at which there is some synchronization.
And what kind of concurrency control do you use for transactions?
So if you look at the overall database engine, it's InnoDB, MySQL InnoDB. So we satisfy the exact same model, snapshot isolation. You can also do serializable if you specify that. All for isolation level.
Decommitted, clean uncommitted, serializable snapshot isolation.
So if you think about it, the storage system doesn't really care about any of that transaction logic. The storage system is just offering to write log records and read pages. That's all it does. So all of that logic is exactly the same as it exists in InnoDB. It's an MVCC-based system, so writers are not going to block readers. If you want to go and read it, you have to read the earlier version. The existing logic is going to go from the undo segments and read the record there. If those pages are not there in the cache, then you go. The undo segments are also written to the storage system, just like any other piece of infrastructure. So everything from a transaction isolation model doesn't change. It's the usual semantic. So I talked about the I/O traffic in the database engine itself. There's a similar, you can talk about a similar model of how within the storage system, which is, like I said, an independent system, within the storage system, the actual storage flow works. So again, this is probably a slightly simplistic representation, but fundamentally, for any given segment that is receiving a log record, there's an incoming queue, and so the records, as the log records come in and they're added to that incoming queue, once they get persisted, we can issue an acknowledgement. And then there's a whole bunch of other steps that happen. A hot log, which is used to serve peer-to-peer requests, the data blocks itself, the backstops. It's not that we only maintain the log records, we also maintain a backstop for any given page. And if the set of log records, the chain of log records for a given page exceeds the size of what the backstop would be, then the logical thing is to actually coalesce it. And so all of that also happens, but they can all of the coalescing stuff, all of this stuff, gossiping with peers, coalescing, all of that can be done asynchronously. And so the goal is that all the steps are asynchronous, only steps 1 and 2 are actually in the latency path. And so long as you can separate that out, which is kind of a key point of the design of the database system, of the storage system, you can keep the flow going of log records. So we're trying to do is get durability, write it down quickly, make sure you can it's durably written, and then issue the acknowledgements. And everything else can be done asynchronously.
So the peer-to-peer gossip is for replication?
Yes, because for instance, for a particular storage system, lost connectivity with the database engine. Right? It didn't get a bunch of log records. Then it needs to, or for instance, maybe there's a partition, a network partition, complete AZ. You need to. So in all of those situations, the storage system continuously gossips with has a protocol to figure out what are the holes and goes and fetches those holes.
Because on the right, the database will try to write to a couple of replicas to get the quorum.
Actually, the database system writes to all 6. As far as possible, we try to write.
Waits for 4.
It waits for 4. As soon as it hits 4, it moves on. It doesn't wait
This is
anymore.
for fixing everything.
It's fixing everything else. We do retries. It's not like we do a write and then we don't hear, we give up immediately. We'll do some amount of retries. It's a balance which we had to tune. Initially, we were more aggressive in saying discarding the storage system, that if you don't hear from it. But what that did was actually added load on this side. So that's it's a bit of fine balance that we had to play with in terms of maybe we're better off actually trying a few more times, and that leads to an overall better outcome. I didn't talk much about the read replica yet. I briefly alluded to it. So Aurora is still, as of now, a single writer system. There's a single master in the database engine in which you're doing writes. But we want to support read scaling. So again, let's look at the counterfactual, how people do read scaling today in the MySQL world. You have a MySQL master typically, and you have something called bin log replication, where you are sending a stream of effectively SQL statements that are applied, in the replica. This is single-threaded. It has significant limitations in terms of it's a source of errors because it's not at the physical log record basis. And so also every change that actually happens in the master has to be applied in the replica as well. And so you're paying for your storage twice in the traditional model. And so your full write workload on the master has to also be satisfied on the replica, which means you have less cycles available to satisfy reads on the replica. So two big problems, or three big problems. One is bin log is a source of pain because it's at the logical level. Second, since you have to satisfy the full write workload, you have less bandwidth to actually do read scaling. And third, you have lag, and often bin log lag can be, can be in the order of minutes, or certainly seconds at the minimum. And so that makes it very hard to give read after write semantics. And so typically, people in the MySQL world are lucky really to be able to use replicas more for availability, that if the master goes down, they can switch to the replica, and not really to scale reads, which limits your overall scalability of the system. So in Aurora, we have a different architecture. We have a master, and we support up to 15 read replicas. All the replicas are mounted on that same 3AZ storage model, the same custom storage system. The log records that flow from the master to the storage system also flow to each of the replicas. And in the replicas, we actually do a form of selective log apply. So in other words, if there is a page in the cache of the replica, because you're satisfying read requests for that particular page, if there's a page in the cache of the replica, and the log record involves that page, then we'd actually apply that log record to that page. If the log record refers to a page that's actually not in the cache of the replica, we can just discard it. We don't care about it. If the request comes in from the reader for a particular page that's not in the cache, we can always get it from the shared storage one. So because of all of this, you get a lot of benefits. First, it's at the physical layer, it's not at the logical layer, so you don't have to deal with a lot of the pain of bin log replication. It's actually, by the way, really a pain. We've seen production situations where customers do things like insert into table values and now, the timestamp function, of course, means that you're applying now on the replica, it's not actually the same time and your histories have diverged, so you don't have to deal with things like that. Replica shares storage, so you don't pay for storage twice. And all you're trying to do is keep the cache as close to the master as possible. So you can get remarkably shorter latencies. We really shoot for 10 to 20 milliseconds lag of the replica. And so now you can actually use the reader to scale your read workload. So it gives you a remarkably different way to do scaling than in the traditional MySQL world. There is a protocol that has to be carefully implemented if you think about it with respect to snapshot isolation. So we are sending continuous information on the durable point that is actually known only in the master. So that information has to be propagated to all of the replicas. And that is used for a replica to set a read view anchor. In order to know, I'm saying I'm doing read for snapshot isolation, I'm doing reads as of this particular LSN. It is also used in, similarly, the time at which all the transactions in the reader were started is also has to flow back to the master, so that the master can also know when it's safe, to get rid of records from the rollback segments, the undo segments. So there is actually, it's a little more complicated than just the picture that's shown here. There's a careful protocol that is actually built in order to make all of that stuff.
So how much more data do you usually have to ship between the nodes for physical versus logical logging?
Bin log versus the actual thing? I think that depends. Do you have an answer for me?
Yeah. So traditionally, if you look at the bin log side, either you will be doing at the statement level or you will be doing the full data. Here we're just talking about the logs actually. So logs are usually very small subset of the actual data. So.
No, but compare with bin log, the SQL, the size of the bin log versus the size of the redo logs.
And I'm just saying that the size of the bin log is significantly. I just don't have that number.
And how do you do like splitting of reads?
Splitting of what?
Of the read action that you need to do? So you're saying like you scale up the read by somehow splitting across different.
So it's up to the application, right? The application can send read requests here, can send, all writes must go to the master, but reads can go out there. It does lead to an interesting architecture from read scalability that we are discovering. One of the things that you can do is effectively do, think about the cache, right? You can think about the cache as being driven as an application driven sharding, if you will, right? That if you can make your application traffic a little sticky to send all requests for for a given source user to a given replica, then you effectively shard the cache amongst your set of replicas. And if you do that, you can actually get effectively a bigger cache. That helps a lot. And if you don't do that, that also means that you're having a more focused. Your apply logic is is also faster because things that don't apply to the cache you just discard. But all of that effectively is at the up to the application. We have collaborated with MariaDB to have a new JDBC driver, which is smart in terms of things like dealing with failover. So I didn't talk much about failover, but if a master dies, any of the replicas can at any time be promoted to be the new writer. And then AWS has a system called Route 53 for DNS. We will automatically switch the cluster write virtual IP to the newly promoted writer. But that takes time. That takes an extra 15-20 seconds. So from the JDBC driver that we've collaborated with MariaDB on, that has the ability to, in case of failure, quickly go and probe each of the replicas to see, are you the master? Are you the master? And cut short the whole Route 53 DNS propagation time. So that's pretty much the only thing really we've done there. There is more work we can certainly do along the lines of, can you make the driver smart to automatically say, I'm sending read queries to the reader, and you can do things like, I think SQL Server does things like this, where you can send read queries, by default just keep sending it to the reader until you actually hit a write. Of course, you run the risk that you begin a transaction, send a few reads, and then as part of the same transaction you do a write, and then you're SOL. But that's just certainly a trade-off there.
So also no question. So if the master fails here, one of the readers will take over as the new master, so it's going to then just go to the storage, read the log to figure out what to undo.
Correct, you're right, yeah, exactly right. So I didn't talk much about, I will talk about recovery, but effectively when the reader becomes promoted to a writer, it effectively restarts and does the normal recovery processing. But if you think about normal recovery processing, the storage system really doesn't care who is doing recovery. And all the state is in the storage system. So one of the beauties of our system, which I think I'm going to talk about, I don't know if I already missed it, is that, I'll get to it in a second, is you don't have to do any redo recovery whatsoever. You only have to do undo recovery. So, and that's because of this log structured nature of the system. I'll actually explain that in a second because I think it's a really interesting aspect of the architecture. But undo recovery essentially means when you restart, you end up reading the rollback segments to figure out what were the loser transactions, what are the in-flight transactions when you crashed, and you have to build up that state in order to then do normal undo. But that can easily happen whether the reader does it or the original writer does it, doesn't matter. It has to be a writer that does it, but it can be the newly promoted writer too. Let's see. Another thing that we did in Aurora, I mean, actually stepping back a second, I talked briefly about things like asynchronous group commits. But when we went to this model of 3AZ storage where you're only writing log records, we changed the rules. It's no longer a database, an OLTP system that was fundamentally IO bound. And a lot of the overhead actually, from a throughput concurrency perspective, were actually in the database engine, and partly because MySQL has a lot of things that are not ideal. Things like global mutexes, pretty a thread per connection model, a poorly implemented query result cache. And so we really attacked many of these with a lot of vigor. we rebuilt the entire lock manager. So one of Alan Beckett's students, Young-Soo Jung, rebuilt the lock manager, completely weight-free implementation. Kamal here actually built the thread pool for Aurora, and so it's a completely re-entrant system. You don't have any more any connection really between the connection and the thread. There's a kernel space epoll that multiplexes the requests that come in on the network. If a thread is blocked on pending I/O, then when that I/O is satisfied, the next available thread will continue where it left off, and that particular thread is free to go and do something else. So it really, again, if you go back to one of the key principles that underlies a lot of what we did, the more we can do things asynchronously, but still keeping track for consistency purpose, the more you get. And doing that at the thread pool was really big benefit for our system. So the lock manager, the thread pool, and also the query results cache were three of the big things that really helped us have a lot more scalability, a lot more throughput at the database engine level. So that now the database engine is keeping up really with the storage system, which is not, it's normally the other way around. But, so moving on now to availability, right? So I think I covered a lot of how the storage system exactly does availability, but one of the interesting things that you get from continuous backup is that you have the ability to do point-in-time restore. So this turns out to be really valuable. You can, if you have an outage or you have a particular problem, or for instance, you have customers who really need to restore an earlier version of the database for testing purposes. It's really easy in our system because you can just do a point-in-time restore to a previous time. I talked already about how backups, taking backups are continuous. You can label the backups, you can label a snapshot at any point in time, so that's a constant time operation. It's just saying, mapping a given snapshot name to a time and therefore to an LSN. You can always at any point of time say, I want to restore to a particular backup. And you just go get these log records and the backstops have been written to S3 and create a brand new volume and then start up an instance associated with that volume. So point-in-time restore is really helpful. It also helps to guard against things like application corruption. So for instance, a user goes and deletes a complete table instead of deleting only a particular record of a particular table. That's application corruption. And in the normal course of time, all of that will be quickly replicated to all the instances. But now you can do a point-in-time restore and go back to that particular point in time. And one of the interesting things we want to do, we haven't yet implemented, is do a copy on write implementation. Right? So if you can think of the new volume implemented with copy on write, you can have essentially instant flashback. You can do an instant point-in-time restore, and effectively you can think of it as histories diverging, timelines diverging. And over time on demand, you can slowly start. You can when things actually change, you actually make the copies. Otherwise, they have multiple volumes operating on effectively the same page. So a whole bunch of interesting things come from this architecture. Crash recovery, I alluded to this briefly. If you think about a traditional database crash recovery, when the system recovers after a crash, you effectively have two problems to solve. You have the case of pages that had committed transactions that never actually made it to the page because it crashed before the page got written. And you also have the case of uncommitted transactions that actually did make it to the page, into disk, before the crash. And of course, you have the third case where you have committed transactions, a given page having both, where the uncommitted transaction actually made it, but the committed transaction did not make it. And the traditional model is, since the time of Aries has not changed much, you go from the point of time you look at the last checkpoint, then you have to figure out how far back you have to go, walk through the redo log records, apply all of the redo log records to rebuild effectively the state of the database at the time of the crash, and then actually do all the undos if you have an Aries style algorithm. It was particularly worse in the MySQL world because the actual applying of redo log was single threaded. A lot of IOs. It was really painful. Recovery could easily take 15 to 30 minutes, depending on what is actually going on in your workload. One of the beautiful things. And if you can step back actually and say, if you think about it, the reason for doing all of this is the database system is persisting two separate structures. The write-ahead log is the structure that's persisting for durability and recoverability. And the actual format, the pages for the B tree and the heap file structure is how it's actually persisting data for performance. And the problem is these two get out of sync. If you take the classical database crash recovery guy's perspective, the log stream is actually the database. Everything else is just a cache. And in effect, that's really the system that we've built. The log stream is the database. It so happens that we've figured out how to unify these things and figure out how to actually give you a high performance read path, even though you only have the abstraction of the log stream. And if you think about it that way, what we're talking about, what happens in redo, is essentially what happens now on normal reads. Normal reads are effectively, taking the backstop, applying the log records, and returning it. That's whether it happens. It's just a normal operation. There's no specific redo recovery that you have to do anymore. And this is a huge benefit of Aurora. You still have to do undo recovery, but once you've built the resurrected transactions, the list of loser transactions at the time of the crash, you can open up your socket for business. So recovery has gone in our system from a world where it's 15 to 30 minutes to something which is more like 15 to 30 seconds. So it's a huge benefit for our database system. Primarily because of this architecture that you completely get rid of doing redo recovery, and you only have to do undo recovery. So again, it's one of those things that this simple idea that if I take the logging storage system, treat that as an independent microservice and separate out concerns, and you pick that right abstraction of only writing redo log records, a whole bunch of things that pop out of it. Read replica scaling, dramatically faster recovery, easy backups. A lot of things all pop out of that fundamental architectural idea. A couple of other things that we did that's interesting. One of them is in the database engine, we actually moved the cache, the buffer cache, outside the main process to make it survivable. So the cache remains warm even after if the database crashes or the system restarts. And so it lets you, the database system restarts, not of course the entire host restarting. But it really, in the event of a crash, it lets you get a warm cache back fast and really makes effective crash recovery even better. So if you didn't do this, it would take longer first to build that resurrected transactions, because all of those rollback segments would be fetched from the storage system, from the network. But it goes beyond that. You can say I'm done with crash recovery and my socket is open for business. But if all the read requests are actually going to be served entirely from the database, from the storage system, it's going to take a while for that cache to actually become warm again, and for you to get real availability, as you're getting kind of a false sense of availability.
How often does the database crash without the whole system, the machine crashing or something? So how often does it happen that the cache survives and the database crashes?
It can happen fundamentally because of two things. One of them could be a bug in our code that can cause a crash. Second thing is there are cases effectively where the replica is not able to keep up, for instance, with the load, where we might, or we have a particular situation where we have something called a stuck item, where effectively, let's say you lose a complete AZ, and you're not actually able to, and you lose one or more nodes in the remaining two AZs. And now you're not able to meet your write code. These things can actually happen, right? And at this point, you start queuing up your writes. And at some point, you're not able to make progress anymore. And then there's a monitor thread that will say, okay, I'm not able to make progress anymore. And then you can actually kill the database. So there are situations when it can happen. They're not ideal situations, but they can happen. In our managed system, a user application cannot actually log on to the instance. So users cannot really issue a kill-9. But there can be legitimate bugs. There can be bugs that we've inherited from MySQL. But there's also, I think, a more interesting case. There is patches. We push to production, right now every month, but we are hoping to get to push to every 2 weeks. When we apply a patch workflow, we update the bits on the page for the actual code, the binaries, and then we have to restart the system. And we restart the system so that it gets the new bits. And so this is something that we do expect to happen, roughly once a month at least. And so it's a non-trivial case where even if there are no bugs, you still have to deal with the warm cache. There's also, for interesting reason, we actually have allowed users to simulate crashes using SQL. It's, I think, a really interesting idea. Our perspective a little bit was influenced by Netflix Chaos Monkey notion, which I'm sure some of you have heard of, where you try to say, I want to be able to insert failures in my distributed system, even in production, to make sure my application can actually deal with it. And so our perspective is Aurora is a highly available system, so we want to provide users with the ability to go and create various kinds of crashes, so they can simulate failures of networking, failure of disk, and actually even crash an entire instance. So users are free to do this through SQL. They can actually easily crash the system. And certainly that on restart again will require us to have it helps to have the warm cache. This hasn't happened that much, although recently we have got a few alerts where we're trying to figure out why the system crashed, and we realized that there are enough users who have started playing with the docs and have found this feature. So we have talked about the feature, it's hidden. The whole point was for users to use it. But what we didn't, I think fully anticipate is the support implications of that. When the system crashes, we are going to look at to see why it crashed, and then we have to discover that actually this was a user-initiated crash as opposed to in which case it's okay. We just clear the ticket and move on. So a few things we didn't quite get. Alan?
So a question about so just now you're saying how if a replica cannot keep up with all the writes, then you just kind of crash the database. I mean,
crash the replica.
Crash the replica. So is that helping in terms of keeping up with the load, or?
No, I think ultimately a lot of this is workload dependent. There are going to be cases where a replica cannot keep up.
Right.
So the question is, there's a multi-fold approach to addressing that situation. One is there a particular reason in this particular case? Is there a legitimate bug? Is there a performance optimization we can do? Is there a source of contention? So that's one vector of things that we would do against that. And the second kind of thing is it not keeping up just because I'm somehow able to sustain so much traffic on my master? So for instance, one good case we discovered was the master was said to be a higher instance size, which is able to handle a much higher workload. But the user set up a replica as a smaller instance size. And so then, the replica just, had enough of a cache, but was not able to keep up again. So that leads to, I think, other interesting approaches that we can take. We've considered, should we build a tiered replication model, right, where we, you don't just have a single master fanning out 15 read replicas. Can you find some other way to have intermediate nodes that then further fan out the log stream? So it can happen. Some of it, I think, could be legitimate issues that we have to fix. Some of this could be particular user configurations that we didn't fully anticipate that can still happen. Do you have anything to add to?
Yeah, the only thing I would add in general, I think that if you look at, for example, binlog, and if you have to support this kind of transaction rate, you will easily run into days worth of lag over the time. And the replication right now what we have is it just works fine for most of the workloads. There are specific workloads where you can have contention. Clearly they can work and be done, and we know what to do over there. And as Sailesh mentioned, basically we can do things around how to make it optimized and also how to change the model around it so that we can do it, share the our stuff, spreading sending the log notes.
I see.
So, picking 15 read replicas is a fairly arbitrary number. We could keep growing, we could say 32 read replicas, or, at some point, there's just, a single master just is not going to be able to, you're not going to have enough capacity. So whether that's at 15 or 30 or 5 is really workload dependent. But the point is, once we allow users to have that capability, they can set up different configurations and they can hit a workload that actually causes a problem.
And just to be clear, in production we set 15 milliseconds. So that's our limit. So if you are off by 15 milliseconds, we just crash. So we are not talking about seconds or days or something like that. We just talk about.
If we say the replica is not able to keep up, to the master, then we will deregister the replica.
I see. Or if I'm the application and I keep seeing 15 periodic crashes, then kind of the sign saying that I can't have overloading the.
Correct. That's the other. Yeah.
I see. Okay.
So another thing when you crash, so you have the master. The master receives write requests, processes, generates the log record, sends them to the storage, sends them to the other replicas. The replica applies everything it needs to apply to its cache. Let's say it's not able to keep up, it's going to restart itself. But when it restarts, the cache will be warm, but at this point the cache is outdated.
Yes.
So the cache has to know that it's outdated and has to validate the
Replica will
request.
send the request to the master to basically say, I'm starting from this point, please give me all the stuff I missed and I will apply it.
Before it can.
Before it runs. Just do note that while we need durable write quorum to commit the transactions, we don't really need that the replica, we're not waiting, the master is not waiting on the replica to actually apply the rights in our projects. So that's entirely our topic. Okay, so let me show some data. So the higher bit is if you run Aurora on the MySQL sysbench, which is the normal benchmark that people use, we're able to sustain a write performance of over 100,000 writes a second and a read performance of over 585,000 reads a second. And if you run that same workload on vanilla MySQL without mirroring, without all that DRBD stuff, that is to make it as easy as possible for vanilla MySQL on that same hardware, this number will be 20,000 writes a second, and this number will be 100,000 reads a second. So the bottom line is that it's a 5x performance improvement in terms of throughput that we're able to satisfy. You're all welcome to reproduce these results. There is there's a URL. You can get exactly we provide an ARMY machine image where you can actually get the complete benchmarking tools. I'm happy to provide anyone who cares specific Aurora credits that are different from your AWS credits, and you can easily reproduce these results and try them on your own. There is a particular client networking configuration, but that's already there if you use our ARMY. That helps. So going beyond benchmarks, the point of the end of the day, your mileage is going to vary. Your actual workload may be different from the sysbench workload. You have noisy neighbor issues. So in the end of the day, if you have a real application, you should actually try it and see. But there are various ways that we've looked at to see going beyond what say the benchmarks, standard you do with the standard benchmarks. And one of the interesting things is looking at what happens if you have very many tables. When I worked as an engineer in the DB2 team 15 years back, the biggest size database would be like PeopleSoft implementation with about 18,000 tables, or SAP implementation with 35,000 tables. Nowadays in our cloud environment, it's not at all surprising for us to see customers with 100, 150, 200,000 tables, and even more. And I was a little shocked when I first saw that. I was trying to unpack why would a itty-bitty, and these are small customers, why are they having 150,000 tables? And so I talked to one of these guys, and it turns out to be quite interesting. Many of these guys are running small SaaS businesses. Could be anything. One guy is running a summer camp management system of talk about something prosaic, right? And for each campsite that he manages, he has a complete copy of the entire schema. That's their model. It's not like a Salesforce style single big multi-tenanted model. So having lots of tables, lots of different schemas is actually just a real world fact of life today in the cloud. That's how people are building these systems, because it's much easier for them to treat the unit of tenancy as at the schema level than to do say what Salesforce did. So if we can provide a system that actually handles those kinds of workloads well, that's very, very useful. So it turns out that if you have a very large number of tables, you actually get, we're comparing again Aurora with running MySQL, whether on provisioned IOPS storage or on local SSD, and we still see significant performance improvements. Similarly, you could just increase the data set size, and you'll still see even all the way up to 100 gigabytes. You still see very big performance wins. But even if you go up to 1 terabyte, you actually still see there's a drop off, but you still see a fairly significant performance win against regular RDS MySQL. You could increase the number of user connections. So one of the interesting things is if you take vanilla MySQL, you will top out on about 250 connections, something like that. On Aurora, in big part because of the work that Kamal and his colleagues did with the new thread pool, the lock manager, and the query results cache, and actually many other things we haven't talked about that we really addressed issues of contention. We can satisfy over 5,000 connections on that same instance. So it turns out that it's important for us to be able to satisfy so many connections, because that's what lets us add much more load, and you get the benefit of the throughput and the asynchronicity. So the more load we're actually able to sustain on the database engine, the more that we're actually able to benefit from the rest of the application. So big benefits in having concurrent connections. In terms of read replica, I briefly alluded to this before. We're talking about lags in the milliseconds, scale versus lags that are effectively in the minutes. This is a huge benefit again to offer, like I said, read after read after write semantics, where I can do a write on the master, and very soon after that do a read. And I write a shopping cart, I want to do a read, I actually want to see that thing. I don't want to see nothing that got into the shopping cart, right? Classic example. You can actually do that and scale the read after the read. Finally, Aurora is deployed to AWS's RDS infrastructure. It's a new engine that RDS offers, and that gets a lot of the usability benefits of a managed database service. It's really easy to create a database. In a matter of minutes, you can get a database up and running. We take care of patching, applying security updates, and things like that. If you want to do a scale compute, say you want to go from a smaller instance type to a bigger instance type, you just push a button, and we effectively get a new host. And because all of the storage is anyway in the same different storage system, you just get up, you're up, up and running immediately. Continuous backups as well as failure detection and failover. So all of this stuff, a lot of this stuff, which either you have to build tools or you have to have a human DBA, we completely take away all of these things. Some of this stuff may be less interesting to research audience, but actually I think if you think about a lot of the benefits, in particular if you think about storage management, I think a lot of the simplicity that we get in storage management is really because of the new architecture. I mentioned before, not having to provision storage is a very big deal for customers, because you end up having to over-provision in big part because if you did not over-provision, you actually have to fail over and you actually lose availability while you then have to go and provision new storage. And so people really have to pay a lot more money just because they want to avoid the pain of downtime. Just because I didn't provision. Completely taking away this notion that users don't even have to provision I/O is a huge benefit. So you're going from the world of where you only got those benefits at the infrastructure as a service layer to a world where you're actually starting to see these benefits in the platform layer. But I argue that you're only getting these benefits because we started off with kind of a different design. So just making a point that even these fundamental system infrastructure ideas has huge benefits for something like usability, which kind of as researchers I think we tend not to think of as much, but actually can be a big benefit. Creating snapshots, being able to get backups, all of the stuff that I talked about, is really useful. I didn't talk much about the storage system, primarily because it's another team, a sister team that builds it, but they handle a lot of hard problems in terms of automatic restriping of the data, repairing mirrors. There's interesting work that they have to do in hotspot management. We also implemented encryption at rest that is coming out very soon. So there's a whole bunch of very interesting work even at the core storage system. And again, if you think back to our architecture where we effectively separated the storage system as an independent microservice, hard to call it a microservice when it's about 1,000 nodes, but effectively when you did this thing, from an engineering perspective, it let us build out those features separately with relatively little interaction. That has really helped us just get some velocity in development kind of engineering. So that also I think really helps. Encryption, we have an architecture where we effectively support encryption at rest. So the all the log records and the backstops that are actually lying in the storage node are all encrypted. And we need this for various different enterprise customers who have these demanding requirements. Aurora is only supported on the VPC environments, so means the clients and the server need to be on the same VPC. So there's a lot of effort into authentication and security. I guess that gets me to the end of my talk. I think there's a lot of information that we have out there. You can go and try it, and happy to help anyone who wants to play with it. We totally welcome it. Thanks for the opportunity. I think from a conclusions perspective, I just go back to that big idea I started with. And I think it's a really intriguing idea that if you think in the cloud, if you think from the perspective that I have an unlimited amount of resources, I think that's a great starting point for rethinking how to build database systems. And so I find that inspiring. I hope that's also exciting for you guys. Thank you. We are hiring, by the way, and we're, of course, partly I think this is interesting work, but I think we have a really fun environment, and we're looking for anyone who makes internships, full-time positions. Don't want to take people away from the research path. That's an important path too, but it's a great experience. So please do send me a resume or contact me if you're interested. Also, we'd be happy to host people who want to give a talk if you have interesting work that you want to give, especially relevant to kind of storage or OLTP systems or anything else. Storage or OLTP systems, my group would be happy to host you guys. If it's something else, we'll find someone else. We're happy to. We're really willing to, love to host you guys if you want to come and give a talk.
Thank you. Thank you. So since we're out of time, let's stop here, and then let's take questions offline. So now we'll transition into the kind of student session. Thank you.